AP Calculus students. We are working on section 3.5 today. That is called limits at infinity. The reason why we're doing section 3.5 is it actually should have been in chapter 1 with limits. And sometimes on the AP exam, when you're asked limit questions, it also includes 3.5 in it, as it should. Again, this is called limits at infinity, meaning this time the x is approaching positive or negative infinity. We call those horizontal asymptotes. If you remember that, look at me, I'm a graph. And as x approaches infinity, this way, if we found that a function flattened out to a certain value, we called that a horizontal asymptote. Now we're saying that it's also called in calculus, the limit as x approaches infinity as we go to the right, or as x approaches negative infinity as we go to the left. So, again, why are we jumping in 3.5? We already covered that. So, here are our notes for today. Here's what we're mainly going to use that I had you memorize from your memorization quiz on limits. This is an incredibly useful limit. We are going to use this a lot today. The limit is x approaches in positive or negative infinity of a constant divided by x to any power. This could be the power of 1, 2, 3, right? But the numerator is a constant, does equal 0, right? This makes sense. I'm going to write a little bit right here. It's not for this problem. It is just for this limit right here. If I make my constant 1 and I divide by x, if x is 10, notice we have 1/10. If x is 100, right, I'm making x approach infinity. 1/100th, 1/1000th, right? Notice that this fraction is approaching 0. So you'll see how we use that in this section. Now, just so you know, the limit as x approaches positive or negative infinity of any of the 6 trig functions does not exist due to oscillating behavior, right? Sine just keeps going up and down between 1 and -1, so does cosine. Tangent from infinity to negative infinity, right? So none of these limits exist. So notice that all of these examples are rational expressions, and so that's what we're going to be looking at today. So the question is, how do you find limits that do exist of rational, that would be a numerator over denominator expressions, of an indeterminate form, meaning when you try direct substitution of infinity here and here, you get positive or negative infinity divided by infinity, which is indeterminate. So you'll see in each of these problems that we can't use direct substitution, but if there is a limit, how do we find it? So there's 3 different ways to do that. A, we could use polynomial division followed by direct substitution of positive or negative infinity. Notice that that would work really well here to do polynomial division, right? Pretty well. We could divide 3x squared plus 2 by 2x squared plus 5 and try direct substitution as x approaches infinity. We'll be seeing this limit here, right? Notice that would work really well on B. 3x squared plus 2 divided by 2x plus 5, right? But when you come down to C, that might be something that bothers you a little bit, because you would be dividing 3x plus 2 by 2x squared plus 5, and now you see that the dividend, the power is less than the divisor, and you're like, wow, I'm not sure how to divide that. So polynomial division works, but it's not my favorite form. That's why I have a star next to B, kind of, it's my favorite. Here's what we're going to do for each of these problems. We're going to factor the highest degree of the entire expression. So let's look at that. Highest degree of the entire expression is x squared. We're going to be factoring x squared from the numerator and denominator. Here, we're going to be factoring in x squared from the numerator and denominator. Here, x squared also. Here, wow, I'm not sure. There's a square root with an x squared under it, which kind of feels like an x, but I'm not sure. We will check that out later. So we're going to factor the highest degree of the entire expression from the numerator and denominator, cancel and simplify, then apply this limit that you see here. Now, another thing you can do that we'll do at the end, you could simply use some logic that we did in pre-calculus. If the degree of the numerator is less than the denominator, then as x approaches infinity, the fraction keeps getting smaller and the limit is 0. If the degree of the numerator equals the degree of the denominator, like in our first problem here, then basically everything cancels itself out except for these leading coefficients, 3 divided by 2. If the degree of the numerator is greater than the denominator, like here on B, then the limit doesn't exist, because as x approaches infinity, this numerator is getting bigger so much faster than the denominator, and the fraction's also approaching infinity. So some logic really works here. D is L'Hopital's rule, but you need to know what derivatives are to use it. So we will revisit this in section 8.3 and use derivatives to do that. So let's take a look at number 2. Let's start with logic, and then let's work with B. Let's do the algebra. I believe here the limit as x approaches infinity. Notice when you try to use direct substitution here in the numerator and denominator, you get infinity divided by infinity, indeterminate, okay? But notice that the degrees are equal, right? So I think by logic, geez, x approaches infinity. If I put 10 million here and 10 million here, this plus 2 and plus 5, that's not going to matter, right? And now the x squares cancel out. I think by logic, my limit's 3 halves, okay? How do we show this algebraically? We are going to factor from the numerator and denominator the highest x degree that we see, which is x squared. So here we go. The limit as x approaches infinity, I'm going to factor in x squared from the numerator and the denominator. Here we go. 3x squared, when I factor out an x squared, I have a 3. Notice it feels like you can't factor x squared from 2. You can. That would be 2 over x squared. Take a look here. If I re-multiply this out, I would still have a 3x squared. And then the x squareds would cancel out here, and I would still have a plus 2. When I multiply these two terms together, I still get 2. Yes, I can factor an x squared from 2. Let's do that in the denominator. X squared factored from 2x squared is 2. Factored from 5 would be 5, right? I'm dividing 5 by x squared. There it is. So this expression and the one you see here is exactly the same. But watch what happens. Now the x squareds cancel out. Now let's try direct substitution using infinity. The limit as x approaches infinity of 3 plus 2 over infinity squared, which is just infinity, divided by 2 plus 5 over infinity squared. There we go. Notice 2 divided by infinity is a very, very small number approaching 0. Same here. And I am left with the 3 halves I felt I might see logically. Next, on B, I see that the highest degree is in x squared. Using logic, though, it looks to me like, when I try to just get another marker here, it looks to me like when I put infinity in using direct substitution, I do have infinity divided by infinity. But in the numerator, that infinity is being squared. This numerator is growing so much faster than the denominator. I think this limit doesn't exist. How can I use algebra to show that, though? Let's factor an x squared highest degree from the numerator and denominator. See? X squared factored from 3x squared is a 3. We now know that this is really 2 divided by x squared. I'm dividing that out. We now know how to handle that. Here we go. Factoring an x squared from 2x would be 2 over x. Again, notice when I multiply this back out, I have 2x, same thing, plus 5 over x squared. Once again, you can see the consistency that we have here. The x squareds cancel out. Let's do direct substitution. 3 plus 2 over, that would be infinity squared. That's still infinity. 2 over infinity plus 5 over infinity squared. There we go. We have 3 plus 2 divided by infinity approaches 0, and I have in the denominator 0 plus 0. Right? Can't divide by 0. This limit does not exist. Certainly we tried our best. Let's come on over here. Logically speaking, I see that the degree of the numerator is less than the denominator. So even at infinity though, this numerator is getting bigger much slower than the denominator, kind of like this limit right here. So I think that this is going to get pushed to 0. Let's use our algebra to find out. The highest degree I see in this problem is x squared. I'm going to factor it from the numerator and denominator. X squared, 3x, when I factor in x squared, is 3 over x. 2 would be 2 over x squared. From the denominator, I would have a 2 plus 5 over x squared. Notice again our logic here of getting canceling those x squareds, and the limit as x approaches infinity. Let's put infinity in. This would be 3 over infinity plus 2 over infinity divided by 2 plus 5 over infinity. I have 0 plus 0 divided by 2 plus 0, which is 2. I do have 0 over 2, and I said by logic I felt that this limit as x approaches infinity is 0, and it is. Let's go to our last problem. Of course, it's a little different. All right. Notice when we try, I'm going to leave my calculator over there. At the end, we'll take a look at the calculator. Oh, there goes.
Another weird thing going on in the house.
Look at our
Here we go.
Can they still see it?
No.
No. Isn't that weird? Here, hold on.
There's been weird stuff happening here. Enjoy.
Is that better?
Yeah.
Okay. All right, the limit is x. Notice that this is approaching negative infinity because that's what we said we were doing, positive and negative, and we haven't used a negative infinity yet, of 2x minus 1 over the square root of x squared plus 1. So this one's a little iffy. My logic though, here's what my logic is telling me. I think because I have the square root of x squared that this is like an x. So like the degrees are the same. So I think that this is approaching a 2 over 1, or because it's negative infinity, a negative 2 over 1. That's what I think is happening here. Let's use some algebra to find out, okay? It's kind of hard for me to say what the highest degree is. I feel like it's the x squared, but the square root's throwing me off. So I'll tell you what, let's do some algebra that we know. The limit as x approaches negative infinity. So here's my thinking. I'm thinking that I am just underneath the square root right now because I'm a little worried about what's going on here. I am going to factor in x squared from x squared plus 1 just under the square root. So when I factor in x squared from x squared, I get 1. When I factor in x squared from the 1, I get 1 over x squared. Now, my thinking on this is when you have two factors being multiplied under a square root, you can split them up. So my thinking is this is the limit as x approaches negative infinity. I'm keeping the numerator the same. And I'm going to say I can do this. I'm going to call that an x. And the square root of 1 plus 1 over x squared. All I did was what I circled right there. Okay, so I think that I can factor an x from the numerator and denominator. I'm kind of running out of room. So if I do, I might just erase and swing back this way. Or maybe not. Can you still see this?
Mm-hmm.
The limit as x approaches negative infinity. I'm going to factor in x from the numerator and denominator. That would be 2 minus 1 over x, right? And I'm going to factor that x, and that will leave a square root of 1 plus 1 over x. There we go. So I factored an x from the numerator, and there was already an x factored from the denominator. I'm going to cancel here and come on up. And I am going to substitute in negative infinity. So I have 2 minus 1 over negative infinity divided by the square root of 1 plus 1 over negative infinity. Okay, now, don't let this throw you. This does not become a positive, though in a way it doesn't really matter. This, you always do division before subtraction. This is approaching 0. And so this is 2 minus 0 over the square root of 1 plus 0, which is 2 over 1, which is 2. Okay, the limit as x approaches negative infinity of 2x minus 1 divided by the square root of x squared plus 1 is 2. And we said that logically that might be. Let me tell you how you know for 2 reasons this can't be right. This cannot be a correct answer. Why can't it? Let's go back. Let's look at the original picture here. Take a look. When you put a negative infinity into x here, this numerator is negative, without a doubt. When you try to put a negative infinity in here, first of all, it's squared and now it's positive. Plus, you know that this square root has to end up positive. We know that we might be right with the 2, but the numerator is going to be positive and the denominator is going to be negative, right? And so this has got to be a negative 2 as x approaches negative infinity. Where did we lose our negative? Plus, I have it on the calculator here for you, and I graphed it. Can you get a picture of that? Or is it too dark?
What would I do for a picture?
No, you're good. You're good.
Oh, yeah.
It's just, can you see it?
Yep.
Notice as you approach negative infinity, that is definitely a negative 2, not a positive 2. So this is important in calculus. You know, where did we go wrong? What happened? And I'll tell you right here, I'm going to come over to the right, to the left. I'm going to erase this. Here's where we went wrong, people. We went wrong right here. We said that the square root of x squared is x. That's not true. Take a look here. Any x I put in here, if I square it and take the square root, it's going to be positive. Here, this x could be positive or negative, right? So it's not really true that the square root of x squared is x. Did you know that? Let's take a look. Let's say I say x is negative 3 right here. I'm going to put a negative 3 in. When I square a negative 3, I get 9. The square root of 9 is 3. That's not true. It is not true that if I put in a negative x for this x here, that it's going to pop out, that this cancels and leaves me with x. It's not true. It's always going to leave me with a positive answer. Whether or not my x is positive or negative, I had to have the absolute value there on that x. That's where we made our mistake. Did you know that? We have to have the absolute value here, right? So now you can see that what happened is we couldn't really cancel there, that the numerator is negative and this denominator would always be positive, and that's how we get our negative. So it's important to know they would do that to you on the AP exam. It would be multiple choice. One of the correct answers would be negative 2, and they would have a 2 as one of the other answers. So we have to be really super careful with our algebra. That's it for limits. That's it for limits. I hope you enjoyed yourself, and I'll see you soon.
Be safe, kids.